knowledge of quantum mechanics, so I will not. The only thing that I'll assume will be some basic knowledge in linear algebra. So of course, a tensor network would be a network of tensors. And a tensor would be something like graphically can be represented as an object like this. For example, a matrix is a tensor as well. It's got a column index, and then it's got a row index, and then a column index. And graphically, you would represent this as a 2-index tensor. That's why it's got 2 legs. If it's got 4 legs like this, A, B, C, D, then you would call this a rank 4 tensor. So this guy is a tensor, and this dot is the tensor itself, and A, B, C, D are its 4 indices. You can, when you have many, many tensors, and then you can group them together as a network. And the grouping is done through tensor contractions, which is, so a tensor contraction would be something like this. So if you have tensor A and tensor B, they don't have to have the same rank. Let's call this A1, A2, A3, A4, B1, B2, and B3. If it turns out that the dimension of A4 is equal to the dimension of B1, the dimension of an index would be, for example, in the example of matrix would be, so the number of the rows would be dimension of A, and the number of columns would be the dimension of B. If this is possible, then I can form a new tensor who would have free indices like these: A1, A2, A3, B1, B2, B3, where it equals A1, that A4 comes from 1 to the dimension, where you would add A and B, where all these are free indices. But here would have the same index, A4 here and A4 here. So that's a tensor contraction. And graphically, you would represent this tensor contraction by just connecting these 2 indices together. So this would be A and this would be B. And this guy would equal to this guy graphically. So that's the notation. A network of tensors could be something like this. For example, one of the most famous examples of tensor network is called matrix product states. And MPS for short. It's a matrix product state in the following sense. So you have a bunch of rank 3 tensors. And all these tensors will be different. Let's call this A, B, C, D. And then you would contract these 2 index, and then these 2 index, these 2 index, assuming that the left index of B is equal to the right index of A. And then after the contraction, you would have something like this. And then it's a matrix in the sense that all A, B, C, D are contracted as if they're matrices. So it's got basically, for example, for this tensor B, it's contracted on the left and on the right as a matrix. And then this guy, sits here as a free index. So this is the one-dimensional. So this is just a matrix product state. These things are used. So this guy is then an element in a vector space, which is formed as a tensor product. So suppose that this index, let's call this A1, let's call this A0, and A1, B1. Actually, let's call these just small a, b, c, d. And let's call this A0 and call this D0. So this then is a guy in a vector space, which is the vector space of A, tensors the vector space of B, tensors the vector space of C, tensors the vector space of VD, and then of course tensor the vector space of A0, tensor the vector space of VD0. So this guy sits in a linear space which is formed as a tensor product like this. Now, because it's an element in a vector space of such structure, very naturally, if you have a vector space of such structure, then this will be a good representation of an element in that vector space. Turns out that this is a natural vector space for many-body quantum systems. Where this A, B, C, D would be the degrees of freedom in a quantum system. Even though I don't assume you know quantum mechanics, I will tell you that the study of quantum mechanics is the study of linear algebra, where your system sits in a vector space and certain quantum states are elements in it. So basically, you will have something like this. And something which I will not prove here, but rather to say this very heuristically, which is you see that basically, if you view this as the left part, you have two guys on the left and then two guys on the right. Their connection is only through this link. So in a sense, the connection is very weak. And that's the hallmark of a tensor product state, where you can imagine that there are many states here. So basically, there are a lot of degrees of freedom on the left, and there are a lot of degrees of freedom on the right. However, there, in a sense, connection is only through this one link. And this link is weak compared to the fact that there are many number of sites on the left and many number of sites on the right, but there's only one link. And turns out that this weakness can be formalized into something called area let's call it into something called area law. Area law of, let's say, connection. And certain states in quantum mechanics, in quantum many-body systems, precisely satisfy this area law. And turns out that there's a very large class of them, states that satisfy this. And turns out that these are the states which are the most interesting. And they are the states which have the lowest energy. So these are states with lowest energy, or the ground state. Ground in the sense that it's the ground of the spacing of energies. It's the lowest. That's why this guy is a good candidate for describing the ground state of many quantum many-body systems. Precisely because of this weak connection structure. And that's the sort of the basis for many optimization algorithms in quantum mechanics to compute for ground state and other things. So I see that my time is up. So I will not go to 2 dimensions, but only this. I don't even have time for canonical form. But I think the message that I really want to convey is that maybe I should, is that I can first, to introduce a graphical notation of this network of tensors, and second, to tell you that graphically that there is a very weak connection. And if you can, get these, take home these 2 messages, that'd be enough for today's talk. Mm-hmm. I guess I'll end here. So if you have any questions, you can ask me.
Okay, thank you very much, Yantao. Very nice talk. So is there any question or comment? Yes, Hada-san, go ahead.
So you said that the good ground state candidate is this tensor product or matrix product state, but how do you know that, or can you improve then to go beyond this tensor product, this matrix product state? Is it just ansatz, or is there any way to systematically improve this approximation?
Yes.
Yeah.
Yeah. So the question is, I didn't tell you the control parameter in such a network. The most important control parameter in this network is the dimension of this bound. Let's call this L, the dimension of this link. And that's typically called chi. As you see that these are typically the ground state, the ground state of S1, dimension of S2, and so on and so forth. So these are determined by your physical system. These are in a sense virtual, so you can have a L with very large link, and then the dimension of that will be large as well. You can prove that for a finite system. If L is sufficiently large, dimension of L is sufficiently large, the representation is complete. However, that's good. But what's bad is that this sufficiently large is a very strong condition. So the dimension of L will have to go something like exponential of the lattice size, which is not acceptable. So so you would like the system. You would like the system to be such that you have a small L, yet a good approximation. And that happens for states with very weak connection, or so this happens for states with low connection, right? And basically, The terminology is entanglement. Right.
Yeah. So if you know the Hamiltonian, can you tell that whether it is the system ground state is a low connection or not? Is it non-trivial?
If you know the Hamiltonian, generically you don't know whether it's gonna have a low entanglement or high entanglement. However, you know two things. I think this is actually rigorously proved. In one dimension, if the system is gapped, where gapped means that the first, so the second smallest eigenvalue of the Hamiltonian minus the smallest eigenvalue of the Hamiltonian, this gap is larger than 0 as the system size goes to infinity. If H is gapped, then you can always know that the half chain entanglement is finite. As L goes to infinity. This is a very strong statement. And this is the precise statement of the area law. This is proved, rigorously proved, proved in the sense of mathematical physics, not proved in the sense of just physics. In higher dimensions, there's no general proof of this, but there are certain arguments in field theory, mostly. And I mean, that's why people try to study these things in higher dimensions and try to see whether that still holds. And generically, that holds for short-ranged Hamiltonian. So this statement, maybe I should also mention that H also need to be short range as well. Yes.
Thank you very much. Yeah.
Mm-hmm.
Very clear. Yes.
No problem.
Okay, next, perhaps Iritani-san.
Yeah. Thanks for the great talk. And so my understanding is you can kind of visualize the tensor product into a graph, but I'm interested in if you have a given graph, you can come up with its decomposition into tensors from the given graph. You see what I mean?
That is, yes, that is approximately correct. So typically what you would do is that you would have a quantum system which say that it's on a one-dimensional chain. So basically you have all these sides, there are some degrees of freedom. It could be spin degrees of freedom. And if that's the case, then you would have a one-dimensional tensor network like this. If it's a two-dimensional lattice like this, then you can have a two-dimensional tensor network where, basically it's connected like this, and the physical leg comes out of the page. So you can have a structure like this, and this is tensor net in 2D, something called PAPS. I should mention that PAPS is extraordinary. It's much more difficult to deal with than MPS. Yes. Yes.
Okay.
Just because of connectivity.
Okay, great. So these graphs look very regular, like a periodic structure. But if you have a complicated network with no, intuition there, and you can work on decomposition of the network into subnetwork in a similar way as you did here.
Yes, I believe so. Right. Yes. In fact, for an arbitrary graph, of course, you can always do something like this. And what's important is actually the graphical topology of the underlying graph. So of course, it doesn't have to be. So in one dimension, it doesn't have to be like a line. For example, you can imagine that you have a tree structure.
Right.
And in fact, I mean, even though this tree is drawn in a two-dimensional paper, it's actually topologically a lot closer to 1D. So these tree tensor nets, you can write down and then you can deal with them, and they're easier than PEPs, for example, than the two-dimensional.
Okay.
Yes.
Great. Okay, great. Thanks a lot. That's very interesting.
Okay, question from Chinkai.
Yes, thanks for a nice talk. So may I translate your language to DNRG? So if in 1D Hamilton is short range, DNRG should be good.
Yes.
Approximation, is that right? But in 2D, then like the picture you show, PEPs will be more complicated. So DNRG will fail.
So if you have a two-dimensional graph, and if the interaction is also short-ranged, DNRG should still work. In fact,
Sure.
yes. But if you have a long-range Hamiltonian, then it's much more uncertain.
I see. I see.
Yeah. So in fact, yeah. So I will.
I see.
Yeah. So in fact, so this is actually current research. So I'm working on two-dimensional PEPs right now, where you have to deal with this two-dimensional structure and try to find out the ground state and find a computationally efficient algorithm that can deal with. And so basically for me, I know how to deal with short-range interactions, but if the interaction is long-range and in 2D, then I have no idea how you should do it. You know, maybe there is an algorithm, but I don't know that. But yeah, people study.
Yeah. In 2D, DNRG is always hard to do. So that's my concern. And 1D is like you have regular recipe.
Yeah, so depending on the problem. So if the problem is short-ranged and in one dimensions, maybe in two dimensions, then there is a good chance that you will succeed. And if you're interested in the ground states. If not, then you have to be a lot more careful and creative. Yeah.
All right. Thank you.
No problem.
Okay, so any other questions?
Oh yeah, I have one question.
Please.
When you have say kind of the composition law, do you have any way to decompose it? Say composite one, reduce one element or two elements and so on, and there's any definite rule for it? That's one question. Second one is why entanglement appears suddenly there? What happens without entanglement? Is there any difference?
So let me answer your first question,
Yeah.
and then I'll and then maybe the second. The question is a good one. So one is, how do you, in a sense, decompose the structure? Of course, decompose is not a precise word. So I can tell you one style of decomposition or regrouping all this, which is let's just call this our renormalization group RG. So suppose actually in one dimension, this is rather trivial to do. So if you have something like this, then I can simply contract this index so that if I contract this index, now I have a system with, originally it's got 5 legs on the bottom. Now it's only 4 legs on the bottom. It's just that one of the leg has a larger dimension, but it's 4 legs. So I can certainly, and this is basically a coarse graining. That's why I call this a renormalization group that's in 1 dimensions. In 2 dimensions, you can do similar things, but it's not as straightforward, but you can still do it. This kind of renormalization group. In fact, this research field, which is called tensor renormalization group was very popular 2 or 3 years ago. Now it still is. I mean, people are still studying how do you, in a sense, reshape this network in some
By the way,
way.
then, you use many terms like entanglement and renormalization group without any definition. But what you say renormalization means, say, block spin transformation like that. What kind of renormalization you are talking about?
Yes. Operationally, my renormalization is precisely tensor contraction. So basically, if I contract
why is that the renormalization?
What is it?
Why is that the renormalization group?
Why is that
renormalization?
So that's a very good question.
Yeah.
Because once I do that, basically, this guy would be a T prime, right? And then there's a T here, and then there's another T here. Let's call this T1, and let's call this T2. So basically, this T1 and T2 gives you a new T, which is T prime. And you know that this T prime plays the same role as any other T's. That is at least in spirit like renormalization group, where you do some transformation of the system. And of course, at the same time, you also change the length scale, right? So if you also group these two and group these two, the distance is scaled by a factor of 2. So there's a length transformation there. And the underlying tensor has undertaken a transformation which is induced by that length transformation. And to me, that is sufficiently to be called renormalization group. Granted, it's not a renormalization group. It's not RG on Hamiltonians. But it's RG on tensors. But if you examine the arguments of renormalization group, you would realize that there's no requirement that the transformation has to be done at the level of Hamiltonians. If you can do this at the level of tensors upon length transformations and look at how the tensors change and extract how they change, it gives you just the same information about scaling phenomena and everything else.
Yeah, and then you get something new by this kind of abstract idea, something which had not been known before, for example. Do you produce something new by this way?
I'm not an expert in renormalization group in tensors, but I believe you can compute things which is extraordinarily accurate. Things like, for example, I think the world record right now on the iTHEMS model in 3D, I think the critical temperature TC is down to the level of maybe 10 to the negative 11th or number 10 to the negative 12th. This world record is done by tensor network renormalization.
So using this kind of idea, you mean?
What is it?
Using this kind of idea.
Yes, this kind of idea, except it's in 3 dimensions.
Then that's okay. Then you come back to the entanglement. Why entanglement?
Yes. Sorry, can you repeat your second question?
Yeah.
So what's your second question? Can you say that again?
Say you use the term entanglement.
Yes.
Why suddenly appeared entanglement? Suddenly, if some state of the entanglement, entangled, and if you use some kind of operation like composition, then probably entanglement is destroyed. But what do you mean by entanglement there? You use entanglement, right? Without any definition. What's the definition?
Oh, I see. So, right. Yeah, that's why. So there is a very concrete measure of entanglement, which is called entanglement entropy. So are you familiar with this object?
Yeah, it's okay. Yeah.
Yes. So when I say entanglement, I mean that when I say that there's a very weak entanglement, I mean that entanglement entropy between two subsystems is low.
Yeah.
Yes. So by entanglement, I just mean entanglement entropy between subsystems. That's what I mean.
That's okay. Then why this idea appeared in your case? In your case means when you combine these two, like the outside and the inside of the black hole, right? People first use like entanglement entropy there.
Yes.
And in first sense, therefore, your operation is related to this kind of physics.
So sorry, I don't understand. So are you asking why the notion?
No. Say without using entanglement or something, it's okay. But you use entanglement, you should have something in mind, right? Something in mind, as I know.
Yes, I think Yantao mentioned something like left side and right hand side of the systems, the several of them, and pointed out the linkage between.
Or maybe when Corona is over, I'd like to talk to you. Yeah, it's okay.
Yes, sorry. There's a very strong echo, so I can't hear very clearly. That's the issue.
Oh, really?
Yeah, I mean, just the left-hand side and right-hand side, they are entangled. That is what I think Yantao means. Fujikawa-san. Yeah.
Oh, I mean, so I see. Yes. So I think I know your question. So so if you have a system which is like this, suppose that there is 5 spins here, and then there are another 5 spins here. When I say that there's entanglement here, I mean that it's the entanglement entropy between this system and between this system. That's how I do the partition.
Actually, then the ordinary, so-called product or our operation we are used to in the past, there's no need to say entanglement. But now, in a slightly generalized way, entanglement like idea becomes important. That's what you are saying.
Yes, you may say this. I mean, right.
Okay, yeah. That's okay. Okay, fine.
Yeah.
Okay, thank you very much. And if there's no further questions, let's thank Yantao for his superb talk and the lively discussions. Thank you very much.
No problem. Thank you.
Great, and welcome to iTHEMS.
Thank you very much.
And so now, as usual, I'm going to make a breakout room, but is there any announcement at this point?
Well, yeah, Yantao didn't introduce himself, but you are a new postdoc, and then you are now in Berkeley. That's
yes. So maybe a brief introduction is
okay.
Nice. So I recently graduated from Princeton. So I did my PhD there in physics, and right now